All right, so we have out our note sheet. Hopefully you remember a little bit about how we took notes, at least kind of generally last class. We did a very brief overview to that. We have out notes, samples, calculator, something to write with. So just as a review before we get to the actual content, okay, in your notes on the left-hand side, you have objective questions that are listed out. They're questions we should be able to answer when we go back to review for an assessment. Where do we write on these note sheets? Right on the right. Okay, so that should be plenty of space for us. Please do yourself the favor. Please do not work ahead. I understand that some of these problems on first glance may be pretty easy if we have, the knowledge that we need to. But maybe we learn a little bit from our diagnostic. We want to make sure that we have the formatting right too as we go through that process. I want to make sure that we do that, so even though you may say, oh, of course I know how to solve for a hypotenuse, just wait. Hang tight. Okay, so today we are going to do a very brief review of trig concepts. Hopefully, it should be exactly that. It should be a review of stuff we already know. If it isn't, that's A-okay. So here we go. Okay? As you may or may not remember, a trig function is defined as the ratios of the lengths of the sides of a right triangle. So by definition, it is a ratio, a fraction, of the lengths of the sides of a right triangle. We are creating fractions of sides of a right triangle, which is what? The whole. Opposite over hypotenuse, and opposite over adjacent. And adjacent over hypotenuse is all about. We're about creating that ratio and making an equivalent value to it. Now in physics, we pretty much only use the three main trig functions. We only use sine, cosine, and tangent. What are the other three of these six trig functions? Secant, cosecant, cotangent. Okay? Now good. It's good if we know them, but not necessary for the context of this course. So sine, cosine, tangent, for the most part, all we need. Now, because these rules only apply to a right triangle, okay, we're going to define them using a right triangle. Okay, so here is our right triangle on the board where we already have an angle indicated. So therefore, we can identify the opposite, the adjacent, and the hypotenuse. Okay, with our angle theta down here, obviously opposing that is our opposite side. Next to it will be the adjacent, and the hypotenuse is always going to be the longest side of that right triangle. Now, I know you know this, but just a refresher. If theta were not in the lower corner and in the upper corner of this right triangle, what would switch? The opposite and the adjacent side, because it's depending on what is the opposing side and what is right next to it. Okay? Now, the ratios that are equivalent to these values, the ratio equivalent to sine of theta is the ratio of the opposite over the hypotenuse. The equivalent value to the cosine of theta is the adjacent over the hypotenuse. The equivalent value to the tangent of theta is the opposite over the adjacent. So, if we were to go ahead and set them up like an equation, this value should be equal to this value at all points in a right triangle. And the same goes for all of those trig functions. Okay? So, our goal is to be able to define the three basic trig functions for any right triangle. So depending on where that angle is, we should be able to define where those trig functions are going to be and how we can solve for the unknown. Something that hopefully you remember back from preschool is SOHCAHTOA. You guys learned that back in preschool, right? You must have done this in preschool. Okay. I learned that in preschool. Okay? I distinctly remember my preschool teacher telling me about SOHCAHTOA and exactly how it works. Okay? Where we know that the ratio and what it's equivalent to, and we know that the sine is the opposite over the hypotenuse. Cosine adjacent over hypotenuse, and the tangent being the opposite over adjacent. So, okay, so we may have learned things at a little bit different time, and that's okay. We're all here right now, and hopefully it's something we all know. Okay. Now, do me a favor for a second. Okay? It's okay if you're writing some stuff down based on the previous parts of the note. I don't want you to write anything down for a minute. Okay? I want to walk you through the next step of this. I'm going to walk with you through how we derive using the inverse trig functions. For lack of better terms, we have the standard issue trig function set up as sine, cosine, and tangent. We use that as such anytime we need to solve for the side of a right triangle. So, I don't know, I call it standard issue trig functions, whatever it is, the proper term beyond that, whatever you want to call it. That's what we do for the sides of a right triangle. When we need to solve for an angle inside of that right triangle, that's when we have to use the inverse trig functions. Now, I'm going to, for a moment, cover up this inverse sign. If we're going to walk through this process under the umbrella of the sine function, we would start with just sine of theta equals opposite over hypotenuse, correct? Yes? Okay, good. So then what would we want to do, what would we need to do, if we need to get theta by itself? Hint, it's on the board. We would take the inverse sine of the sine of theta to get theta by itself. That's what we would do. Now, algebraically speaking, what we do to one side, we must do to the other. So if we take the inverse sine of one side, we must take the inverse sine of the other. Now, what is the inverse sine of the sine of theta equivalent to? Theta. That's all it is. Okay? So now we have theta equals. We have our equation rearranged. And now that we can put them in terms of all three trig functions, because really we could walk through it, let's write these down. So if you need to solve for an angle, do you need to know how to derive that? No. Okay? But we should know at least this. That if we're solving for an angle and we have to use the sine function, we should be doing theta equals the inverse sine of opposite over hypotenuse. If we're trying to solve for an angle and we have to use the cosine function, we should be doing inverse cosine of adjacent over hypotenuse. If we're trying to find an angle and we have to use the tangent function, inverse tangent of opposite over adjacent. Again, quick recap in terms of what we do. These inverse trig functions are any time we're solving for the angle. When we solve for the sides, we'll use our standard issued trig functions. Hooray, Pythagoras. Also, trig. And I know, I also learned this in preschool. I hope you guys also learned it in preschool. Is that when you learned it? Good, good. Okay. So, absolutely, that there is also a trig with the ratios of the lengths of the sides of a right triangle in relation to each other. And we know that as Pythagorean's theorem, where a squared plus b squared equals c squared. So if we know any two sides of a right triangle, we should be able to find the third. That part of it's not complex, is it? Now, Jackson may not have done that in preschool, but I'm sure, like second grade, at least, I'm sure.
Yeah, second, third.
Okay, somewhere in that range, that's good. All right, so let's transition now to our sample problem. Okay? And again, I understand. I know these problems are simple. Please do not work ahead, because this is our opportunity to make sure that we have our formatting correct. Okay, so we have this right triangle, ABC. Okay, we are given the lengths of the sides A and B. We're going to find length C and angles A and B. So how many answers in total should we have? 3. Okay, let's start at the very beginning. We are trying to solve for C, the hypotenuse. So we need to have a C equals equation. Now, what are we going to do? How are we going to find C? Hopefully this is pretty easy. Pythagorean's theorem. Okay? So what is the equation that we have to write? Well, we need to think about that because you're used to C squared equals A squared plus B squared. What is C equal to? Good. Square root of, and please write it as such, open parenthesis, A squared plus B squared, close parenthesis. That is the rearranged version. Now, if Caitlin wanted to go ahead and say c squared equals a squared plus b squared, do the square root, and then come to that point. That's perfectly fine. I don't lose points for detailing out for you a way that you can help remember what it should be. That's perfectly fine. But the first thing we get credit for is our equation rearranged for what we need. Then the next step is going to be our substitution, where we know a is 12, we know that b is 17. We can substitute directly into our equation. Okay? And our last step, once we have that, let's compute what our answer would be. And the nice thing is, if we've done our legwork and set it up properly, this should be a very easy substitution. Absolutely, Wes, we carry everything out in the thousandth place. So Wes, if you don't mind, what is the answer that you got? 20.809. Now I know this problem, it is not a problem that is provided with units. But if it did, we would need to make sure we had units provided with that. Okay, and that is properly rounded. That is our final answer. Okay, so that's all we need for that piece of it. Now, I know that some of you would say, but Talbot, can I just do a squared plus b squared equals c squared, plug in the squares, do the addition, then do the square root of? I mean, you could, but I need a little bit of faith from you in the fact that I've been teaching physics for a decade at the high school level. I've taught some collegiate level physics. I understand where students make mistakes. And those students that take numbers and plug them directly into original equations, then try to do algebra, will make mistakes. I want you to think about it. You remember seeing number 17 from our diagnostic earlier? And what that response was with the rearranged version? Could you imagine if you had plugged in your values first and then tried to do the algebra? Most of us in here probably would make a mistake doing it that way. So we need to do the algebra, rearrange the equation first, get it set up, then we can rock and roll. Well, in this one, we can't just make up units. It's not provided. Okay? Now, because it's just more of a mathematical problem, that's just the way it's delivered to us. You're going to have units and other problems. 20.81 is incorrect because it's not expressed out in the thousandth place. Our rule of thumb all year, unless otherwise noted, is going to be just thousandth place. There are only two exceptions to that rule, and both of which come in the fourth quarter. Okay? All right. So angle A. Now we have a bunch of different ways to notate this. I'm just going to call it theta with A as a subscript. I'm just going to list this capital A here. That's fine. We technically have all three trig functions at our disposal at this point. But you would be mistaken by using two of them. What is the one that we should use? We should use tangent. Okay? Why? Correct, it is opposite over adjacent, but why is that beneficial? You are given them. That's one piece. Okay? And they're givens as exact values. It's not like it is some sort of rounded value. Okay? But more important to that is 20.809 is a rounded value. It's not wrong from a process standpoint to use sine or cosine, but if we use that rounded value in a future calculation, we are introducing rounding error into that next calculation. And we are going to do what we can to eliminate that rounding error. And especially, they even said it, we have exact values here that are given to us. So let's use it. Therefore, step one, the equation. Are we using standard trig or inverse trig? Inverse trig. So this is going to be inverse tangent of opposite over adjacent. Now, because we are still kind of in math land, at least for today, I know that you can do OPP over ADJ, however you want to do that. I'm just going to simply list it as O over A, so the opposite over adjacent. Technically, since we're finding angle A, that would be here. Okay, we could do side A over side B. Whatever you use, just be consistent with what your diagram is going to state, or with what trig would state. When we get into the physics of it and we're doing this sort of stuff, we will have physics-specific labels that we're going to use for it. So right now, I'm not so concerned with what we do, as long as it works for you. Okay? So then, now we can do our substitution. Inverse tangent of the opposite side, which is side A value of what? 12 over 17. Okay, for those of you that have calculators, pluggy chuggy. Please also make sure you are in degree mode. You're always in degree mode in the context of this class. Okay, what do we have as an answer? 35.218. Make sure we can see the decimal point. I heard it from a couple. Degrees. Okay, degrees would be our units for this one, so make sure that we have that included. Okay. While you're on a roll, why don't you find angle B on your own? Think about what we've talked about what the best solution would be. I know that there are a couple of solutions at this point. What will be the best way to get there? Roman, while we're working on this, why don't you let me know, what did you do? What was your method to find angle B? Roman?
I did angle B equals the opposite over adjacent.
Okay, hopefully an inverse tangent.
Yeah, and then I started.
Okay, opposite over adjacent. Well, actually, it's the same equation as to what we hopefully had in our last part. The only difference is we're now solving for angle B. Now, could you do the whole 180 minus the 90 minus? Yeah. But, keep in mind, what happens if we make a mistake? That would then carry through that response. Okay, and then you're not really giving a whole lot of room for partial credit in terms of what we're trying to solve for here. Are there exact values that we know we can use that are given in the problem? Absolutely, it's going to be our best way. So all that's really going to change here is what? The ratio is, even though it's still opposite over adjacent, because we've switched our location of the triangle, 17 over 12. Pluggy chuggy, and we get a response of, I'm sorry, name again, because I'm still trying to learn. Will, what do we have? 54.782 degrees is Will's response. And I believe that's what we should be getting for them. Okay. Any questions on sample A? Okay, let's roll to sample B. A flagpole creates a 14-meter long shadow. Well, good. We can go ahead and mark that in our diagrams. The angle the tip of the shadow makes with the top of the flagpole is 63 degrees. Find the height of the flagpole. And I'll label the height here as an H. Again, find how you want to label it depending on what you're envisioning. What I'd like for you to do is take a minute, go ahead and solve for the height of the flagpole. All right, so ladies and gentlemen, let's take a look at what we have up on the board. Again, I know it's a little bit different notation than what we've done before, and you may have a little bit different from that. But do we agree, one, that we have an equation rearranged for what we need to solve for? Yes. Do we then have the appropriate substitution? Yes. Sunshine, I'm going to make one suggestion though. And you may like this. Chemistry had you plug in your units along with your substitution. Don't. We're going to simplify that process. You do not put your units along with your substitution. As you can see by some of the equations that we might see, that's going to be a very messy process. Often in chemistry, no offense to chemistry, but a lot of the equations are pretty simple. Okay, obviously some of the stuff you do with it could be more complex than that, but the equations and things they're based off of are pretty direct. We just simply have equations that have 5, 6 plus variables in it that we might need to do some things with, but we're not going to include our units in our substitution. And then we come up with our final answer of 27.477 meters. Does that seem reasonable for this problem? Yeah. Our largest side of our right triangle is opposing the largest angle aside from our 90-degree angle, so that's fine. A 27-meter tall flagpole is a very tall flagpole, but they do exist. One last one. Yes.
So when it says that, like the angle there, the angle here, the theta symbol is.
Yeah. So you do tangent of theta. Just kind of in my handwriting, just tangent of theta, because I usually write it like that. Then when you go to do your substitution, tangent of, what's the angle here? 63.
No, I mean like the 63, like where the theta is on the.
Yes.
I put it up at the top.
Yes. No, because the tip of the shadow, the angle that that makes, tip of the shadow with the top of the flagpole, that's the angle it's here. Okay? All right, one last one. And it's my job as your physics teacher to try to confuse you at times, so I'm so glad that you aren't working ahead. Okay, an eagle is flying at an altitude of 230 meters and spots a rodent 368 meters in front of him. Let's diagram what we know before we read on. Where does the 230 meters go in our right triangle? Is it the height of our right triangle? Yes, okay. That's our 230 meters. What might be a little confusing is where the 368 goes. Correct, it's on the base. Okay, so it's 368 meters along the base of that triangle. Because as our eagle is soaring, it's flying along the horizontal in front of, it is along the horizontal. Okay? Then, okay, assuming our rodent freezes, and our eagle is going to dive, and we're going to find the angle the eagle must dive to grab the rodent. So the question is, where's the angle we're even trying to find? Is it in the upper corner of our right triangle? Yes. Is it in the lower corner of that right triangle? It's in neither of those spots. An angle that the eagle must dive at is an angle of depression, which is that. Now, here's the good news, because we know that is not an included angle. We know some other stuff in the land of geometry, that there is an angle inside that right triangle that is equivalent. And where is that located? Okay, alternate interior angles would tell us that angle is equivalent to the angle that we are trying to find. Now, could you find the angle that our eagle must dive? Good, go for it. Okay, so take a look at what we have. Should we use the tangent function? Absolutely. Okay, based on what we have, that's what we get more often than not. Okay, so we set it up, 32.005 degrees. Is that what we get? Absolutely. Okay, so Jordan, good work with that one. Okay, and so in terms of today, okay, notes and samples, that is going to be it.